All right, so when we were doing derivatives at the beginning of the year, like for the first half of the school year, probably more than half, whenever we took the derivative of something, of an equation, but normally when we're looking at real life applications, that equation represents something, more likely the amount of something. Whenever you take the derivative of something, it's representing the rate of change. Okay, specifically a slope, that you're used to that word. Okay, rate of change or slope. So if we have this particular applicable example, water is being drained from a swimming pool, and R of t represents the amount of water measured in cubic feet, so we're kind of talking about a volume there, that the swimming pool has at any given time. Then the derivative of R would represent the rate at which the water is changing. Remember, we had all those different connections between derivative and original function. If the derivative is positive, the original function is increasing, right? So if the derivative is positive, the rate at which the water is changing is increasing, so you're gaining water. Okay, all those different relationships are still true. So we can represent that statement mathematically. Okay, the derivative of the amount of water is R prime of t, the rate at which the water changes. What would the units of that derivative function be? We're talking about a rate, so we're going to need some type of per unit. Yeah?
Feet cubed per hour squared.
That would be an acceleration. Okay?
Just a rate, right?
Just a rate, like miles per hour, feet per second. Okay? So notice how feet cubed is the unit for the amount of water that we have. But if we're talking about a rate, we need to divide that amount by some time unit. Okay, a rate is something per something else. Okay, acceleration, you get into that unit squared idea. I love it. Now, we've been introducing integrals, aka working backwards. So if you were to work backwards from a rate, that's representing the amount of change in that original function. I'll get it later. That's okay. Okay? So whenever you're integrating, you're looking at how much a function changes from a beginning point to an ending point. That's why we have those bounds. You have a starting value and an ending value. Okay? So maybe let's kind of practice this. We've been talking about particle motion, like at position, velocity, acceleration. If I were to work backwards from velocity, what would that represent? If you were to go one function back from velocity, remember our order? The position, okay? And specifically, if you work backwards from velocity, that's going to represent the amount of change in position. Okay, that's why we do top minus bottom. Whenever you're subtracting two things together, you're finding the change or the difference in those values. I hope that makes sense. What if we were to try this one? What if we were to work backwards, aka integrate acceleration? What would that value represent? Amount of change in velocity. Good. So whenever you're integrating, you can think about it as area under a curve, antiderivative, but the applicable representation, okay, in terms of units, is the amount of change in that previous function. So in this case, the previous function would be velocity. Good. So let's revisit this kind of swimming pool idea. If we were to integrate the rate at which the water or volume is changing, what would we be getting as a result? If we did top minus bottom, if we were to work backwards from the rate at which the water's changing, what would this value be if we actually had numbers to go with it? guys got the idea here. I'm wondering if we can apply it to this new example.
How much water, how much the level of water change?
The level of water or the volume change. Okay, so we'll say amount of change in volume, because our units were cubic feet, from time A to B. So we don't really know what our bounds were if we want to go from the first hour to the third hour or whatever the case may be, but whatever number we get in the end, that's going to represent the amount of change in the volume of water from beginning point to ending point. So integrals, they kind of can mean different things depending on the situation or the problem you're working with. They could represent area under a curve. They could represent antiderivative. But the number value you're getting is also representing an amount of change. So we're going to keep that in mind as we go through some of these examples. So speaking about particle motion, we're going to visit kind of a velocity question here. They give us a table of values for some particle. We don't really know how it's moving, either left or right or up or down. Let's try part A. Approximate the value of the integral of velocity from 0 to 30 using a midpoint Riemann sum. Using correct units, explain what this represents. So, how might you want to break up that table to eventually get your rectangles? We could use 3. Okay, now here's what's a little tricky. They don't tell you how many to use, right? Typically they do. So let's think about this. Couldn't you just make this one big rectangle? Wouldn't the midpoint be at 15 then? Somewhere right there? That's an approximation, okay? You could make this, let's see, 1, 2, you could make it 3, right? Because we have midpoints for those. I don't know if we could make it any smaller than that, because if we did 2s, we wouldn't have a midpoint to use. So which one do you think is more accurate? Should we use one big rectangle or 3 smaller ones? Remember when you were drawing all those rectangles, did you notice a pattern?
Pretty small.
The more rectangles you use, the more accurate it's going to be, because you're including more of that area. You don't have as much overage or underage, if those are even words, when you're shading, okay? So instead of making one big one, let's make 3 smaller ones. So area of our rectangle, the first rectangle would have a base of 10, and the height, according to the midpoint, is 1.6. We can continue that process for the other rectangles we drew. And then some of you might be able to do this in your head, others might need a calculator. We'll go ahead and figure out this Riemann sum. $63. Can we put a unit to it? If you work backwards from velocity, you get feet, a position, right, a location, a distance, okay? So what do you think this 63 feet represents? There we go. Okay, so we're going to write down 2 different things. It depends on how you want to approach this problem. So one thing Braden said, we could say amount of change in position from 0 to 30 minutes, aka your displacement. Change in position, how far you are from some beginning point. Maybe you want to write that down too, displacement. Some of you might want to write down what this means in terms of area. Okay, this 63 value is approximately the area under what graph? Velocity, the function that you started with, okay? So in terms of the problem, okay, particle motion, how it's moving, it's the amount of change in position. You could also say this is the area, approximately the area under the velocity graph from 0 to 30, okay? Remember, integrals can mean multiple things. Area under a graph, the amount of change, antiderivative. You could approach all three of them if you wanted to. Okay, let's go ahead and check out the next one. What is the value of the integral of acceleration from 5 to 25 using correct units? Explain this value. Right. What do you want to try here? Right. If we work backwards from acceleration, we get velocity. So doing that fundamental theorem of calculus, top minus bottom, we could do v of 25 minus v of 0. We should know those values from the table, right? 1.6 minus 1.6. So what about the units on this 0 value? Good, Dan?
Feet per minute squared.
Close. Just feet per minute. If you work backwards from acceleration, you get velocity. So this would be, notice how the 1.6 was a velocity value for both of them? So if you subtract 2 velocity units, it's still a velocity unit. Okay, so there's the value. Explain what this represents in terms of the problem. So we could tackle this kind of 2 different ways. If it's an integral, you could say it's the amount of change. The amount of change in what for this case? Velocity, good. Amount of change in velocity from 5 to 25 minutes. Clearly from the table that makes sense, right? If you start with a velocity of 1.6 at time 5 and you still have a velocity of 1.6 at time 5, the change is nothing. Okay, even though you may have changed in the middle, you're only looking at those 2 points. Or you could have tackled this integral as an area. So what is this 0 approximately? The area under the what graph? Acceleration, right? That was the function in the integral. Area under the, we'll say acceleration or a of t graph. We doing okay so far? All right, let's keep going, trying some more. So this one, the temperature of water in a tub is modeled by a strictly increasing twice differentiable function. Okay, so it's only going up. Do we know what twice differentiable means? You can take 2 derivatives, okay, and since it said differentiable, that also implies continuity. Good. Okay, so it's only going up. You can take 2 derivatives, and it's continuous as well. Okay, so this is the function w of t represents degrees Fahrenheit. So let's check out the first question. Using the data in the table, estimate the value of w prime at 12. Meaning the derivative of w. How might you want to try that? How can we estimate a derivative based off of a table? Slope between 2 points. Which points do you want to use?
15.
There we go. We'll pick a point before 12 and after 12. So throw back to Algebra 1, slope between 2 points. I don't care which ones you use first. You need to be consistent, though, when you use them. Difference of y's over difference of x's. All right, so using your calculator, can we get 1.017? Yeah. Okay, what about units? We took a derivative, aka a rate of change. Degrees Fahrenheit per minute. Perfect. Okay, so using correct units, which we did, interpret the meaning of this value in the context of the problem. So what do you think this is telling you about the temperature at this time 12? There we go. If a derivative is positive, okay, think about your connections. If the derivative is positive, the value is increasing. So we'll say the temperature at time 12 is increasing. You could say specifically at a rate of 1.017 degrees Fahrenheit per minute. But if you just want to say it was increasing, I think that would suffice as well, because you're interpreting it in the context of the problem. So not only is it positive, tells you it's increasing, but the actual number value is telling you the rate. Really good. All right, let's check out an integral. Use the data in the table to evaluate the integral of w prime using correct units. Explain what it means. So if we work backwards from w prime, what should we have? What function? Original, aka just w. So if we do top minus bottom, fundamental theorem of calculus, maybe we can figure out those values. They give us a table. Right, I think we should get 16. What about units? Degrees Fahrenheit. Okay, so in the context of the problem, what does that 16 degrees Fahrenheit mean? There we go. Amount of change in temperature from 0 to 20 minutes. Right, so when you're talking about a derivative, you're talking about a rate. When you're talking about an integral, you're talking about change. Okay, two things that we're eventually going to sink into our heads throughout the rest of this unit. Let's try the last one. For 0 to 25 interval, the function w that models the water temperature has a first derivative given by this function. Holy cow, is that crazy? Based on this model, what is the temperature of the water at time 25? What do you want to try to do? Go ahead. Let's work backwards. Okay, so we'll work backwards from this rate, which should represent an amount of change. What bounds do you want to use for the integral? Okay, if you look at the table at the top, you could use 0 to 25, you could use 4 to 25, 9 to 25, 15, or 20, because those are the specific time values you know for certain temperature of degrees. So it doesn't matter as long as your top bound is 25. So maybe we'll use Braden's 20. Okay? Oh wait, they also told you there. Never mind. That was what they were looking for. My bad. Okay? At the very beginning they mentioned 20 to 25, so you would have to use 20. Okay? So let's go ahead and figure this out. If you work backwards from W prime, we should get W. So top minus bottom fundamental theorem. We're trying to figure out W of 25. Based off the table, we know W of 20, that was 71 degrees. How might you want to tackle this left-handed side? Do we have a graph of this function to calculate the area under? No, but what do we have? Calculator, right? Can you type that in? Go ahead and get a value. We'll round it to 3 decimal places. We are working with trig. Notice how there was a cosine in there, so you need to make sure your calculator is in radian mode. Any takers? 2.043. I like it. What does that 2.043 represent? Change in what? What are we talking about for this problem? Change in temperature from 20 to 25 minutes. All right? So if you know some starting value, like W of 20, we know that's 71, and you know the amount of change from 0 to 25 minutes, we should be able to figure out where we are at the end of 25 minutes. So adding over the 71, looks like 73.043 degrees Fahrenheit. Alright, so the integral could be the area under a curve, could represent antiderivative, but it could also mean a change in value, okay, depending on what type of problem or context you're working with. We doing okay? So far so good, I hope. Let's keep going, we're on a roll. Okay. A pan of biscuits is removed from an oven at some point, we'll say time equals 0. The temperature of the biscuits is 100 degrees Celsius. That might be noteworthy to write down. The rate at which the temperature of the biscuits is changing is modeled by this function. Okay, so they do give you a derivative equation. They tell you, though, at time 0, you have a temperature of 100 degrees Celsius. So maybe we'll write down B of 0 is 100. We can't say B prime because the prime is representing a rate. After all, it's a derivative. All right. So first one says find the value of B prime of 3. Can we use our calculator for that? Let's see, I got -8 point, can you guys fill in the rest? 236, I think I heard it. Okay, what about units? It's a derivative, aka a rate. We need some type of per unit. Love it. Okay, so in the context of the problem, what does that number mean? What can you describe or tell about the temperature?
It's decreasing, it's equal to the rate of.
Perfect. Temperature is decreasing at time 3 at a rate of 8.236 degrees Celsius per minute. Decreasing because it's negative, and then the numbered value is the rate at which it's decreasing. Good, good, good. All right. Next one, sketch the graph of B prime. Okay, so on your calculator, we'll go ahead and hit y equals, and if you have anything in there, clear it out. Let's go ahead and type in the B prime equation. Now, before you hit graph, they actually give you a graph on your paper that they want you to sketch it for. So let's go ahead and make the window on the calculator the same as the window on your paper. That way it kind of looks realistic as to what you should draw. So it looks like the lowest x value is -1, highest x value is 11, and they're counting by ones. Lowest y value is -6, highest y value is 2, and they're also counting by ones. Alright, so we kind of get that little curve there. So let's go ahead and maybe you can roughly draw it on your paper.
Is David Gaspersky?
Not till 7th period. Not till 7th period.
Never mind.
He's in dub.
Oh, he is.
Okay.
Alright, so let's go ahead and draw a rough sketch. If you wanted to be fairly accurate, you could hit trace and bring up that little like cursor or spider, and you could probably plot some coordinate points if you wanted to, just to be a little bit more accurate. But we'll go ahead and just draw a rough sketch. Something like that. So in the context of the problem, why does this graph make sense? Remember, this is the graph of the derivative, B prime. We're taking a pan of biscuits out of the oven.
Temperature will decrease faster, closer to the time to death.
There you go. Okay, so obviously if we take a pan of biscuits out of the oven, isn't their temperature going to eventually decrease until it gets to room temperature? So if it's always decreasing, shouldn't the rate, aka derivative, always be negative? See how it's below the x-axis? Okay. Notice how this value here has a, we'll say, a larger number value, like 5, than this point up here, maybe 3. So 5, what are we talking about? 5 minutes after you take it out of the oven, the temperature is decreasing faster than it did at 11 minutes after being out of the oven. Because the moment you take it out, there's such a big temperature change between oven and room, it's going to cause the temperature to fall more drastically, okay, faster. So we'll go ahead and say that, explain the context of the problem, the temperature is decreasing faster at the beginning since the biscuits are initially pulled out of the oven. Also, since B prime is always negative, it makes sense that the temperature is always decreasing. Alright, let's go ahead and try one more, the last one. At time 10, what is the temperature of the biscuits? What do you want to try? Integral. We're going to work backwards. They give us a rate. We need to work backwards. They give us the rate of change of temperature. We need to work backwards to actually figure out just temperature. So we're going to integrate that B prime of t equation. What do you think the bounds should be?
10 to 0.
Or other way around, 0 to 10. That's fine too. Okay? They give us the beginning temperature at time 0. They said that was 100 degrees Celsius the moment we took them out of the oven. And we're trying to figure out at time 10 what's the temperature. So if we know the temperature at 0 and we're trying to figure out the temperature at 10, we got to figure out the change in temperature between those two times, aka integral. So if we work backwards from B prime, that should represent just B. And using top minus bottom, fundamental theorem, we'll have B of 10 minus B of 0. Alright, so B of 10 is what we're trying to figure out. We know B of 0 is 100. On your calculator, you can go ahead and type in the integral of the derivative function, because they give it to you at the top, and we'll get that value. What'd your calculator give you? Can we find it?
Negative 65.817.
817. Alright, so again, if that's an integral value, that's representing a change, amount of change. So specifically for this example, change in temperature from 0 to 10 minutes. Notice how the change is negative, right? Because the temperature is decreasing. Makes sense all the way through. So if we add over the 100, the temperature at time 10 looks like 34.183 degrees Celsius. I have no clue what that is in Fahrenheit. We doing okay? Is it starting to click a little bit? I hope. All right, we'll stop there for today. We'll save the last kind of free response formatted question for tomorrow as a review. Okay.